we can approximate area on the graphs. Of course, graphs of functions. Number two, we can find exact area on the graphs. Of course, of functions. Okay, right now, we don't know how to find the exact area. We will. So at this moment in time, we are going to approximate area on the graphs. Okay, how do we do that? I cannot go back there. I have to graph it again. So I'm going to graph it fast. No points. You know what I'm doing. You know what area I'm talking about. So this is 0, 1, and 2. And this is, of course, our f of x, which is x squared plus 1. Okay. So first of all, we are going to approximate. So this is approximation. Approximate using two subintervals. And we have, at least at this point in time, three different methods. Using leftmost point. Number two, rightmost point. I'll write them again because it's too small here. Or midpoint. So I'm going to write this again. So here's the graph. So again, area with the leftmost point with two subintervals. The area with the rightmost point with two subintervals. Or the area with the midpoint with two subintervals. Leftmost point, rightmost point, midpoint. Why so many? Why left and then right? And why the midpoint? What is all this? Why so much work? Well, you will see in a moment. What is the area with the leftmost point? So 2. So first of all, I will divide this interval in two equal pieces, from 0 to 1 and from 1 to 2. I will draw a vertical line at 1. I already have a vertical line at 0, and I already have a vertical line at 2. I'm asked to use two subintervals. Okay, here's my one subinterval, and here's the other. What is the base of this subinterval? It's denoted, of course, our best friend, delta x, which is 1. The length here is 1. Of course, the length here is 1 as well. How did I get this? Well, the formula for delta x, which is the width of each subinterval, is determined. Delta x, of course, our interval is a comma b, our best friend from Rolle's theorem and from all the other ones. In this case, it's 0, 1. I'm sorry, 0, 2, of course. So delta x is b minus a divided by n. What is n? Number of subintervals. So my n is 2. 2 minus 0, 2 minus 0. 2 minus 0 over 2 is 1. One more time, delta x, 2 minus 0, divided by the number of subintervals we started with. So that's how we get the width of each subinterval to be 1. Okay, I got that. Now, if I'm told to use the leftmost point, I will create on each of these two subintervals, I will create a rectangle that has the height, the left point of each subinterval. So this is the height for the first one. This is the height for the second one. If I'm using the leftmost point for the graph for the function that I chose, I will add this area to this area. Will that be an overestimated of the exact area or an underestimated number? Will it be an overestimation or an underestimation of the actual area? And how do I write it? What do you think? Will it be an underestimation or an overestimation?
It will be an underestimation.
Of course, because look at all this piece and look at all this piece. So how do I write A with left 2? Base times height plus base times height. What is the height? F of 0. What is the height here? F of 1. So I have base 1 times the height, F of 0, plus base 1 times F of 1. So because this repeats, we will normally write it as delta x, and in parentheses, F of 0, plus in our case, F of 1. So I'm going to always keep it outside. So in parentheses, I only have what I need. So I know that in our case, I don't need to write 1 because it's 1. F of 0. So remember the function is f of x equals x squared plus 1. F of 0 is 1. And f of 1 is 1 plus 1, which is 2. So this is 3. Underestimated. Good. So now we know how to calculate the area, not to calculate the area, to approximate the area with the leftmost point with two subintervals. Okay, so now let's see how we do the same thing with the rightmost point. And then I'm going to ask the same question. So again, real quick, the graph is this. So this is 0, this is 1, and this is 2. Now we want the rightmost point. The rightmost point means this: base times height. Base times height. Will this be an overestimated or an underestimated area?
Overestimated.
Of course. Thank you very much. Overestimated. By this area and this area. So A, right 2 equals base times height, because the base is 1, I'll omit that, plus base times height, f of 2. So f of 1 was 2. F of 2 is 5. So this is 7. Overestimated. So the area is somewhere between 3 and 7. Now let's illustrate the midpoint. Same one, same graph, of course, everything the same. The midpoint. Now careful. 0, 1, 2, 0.5, 1.5. Height. Height. So this and this. I can no longer ask if it's an overestimation or an underestimation, because we don't know, really. So the area with the midpoint with 2 subintervals will be base, which is 1, that's why I'm omitting it, times height, plus base times height. So this is 0.5, so our function again, x squared plus 1. 0.5 squared will be 0.25 plus 1. 1.5 squared will be 2.25 plus 1. So this will be 2.5, 3, 4. 4.5. As expected, 4.5 is definitely between the 3 that we found, which was a complete underestimation, and 7 that is a complete overestimation of the exact area. So one other application of this, I will explain it again later, is I may not be, if you give me this function, I may not be capable of determining its antiderivative. Because if I cannot determine its antiderivative, I will never be able to exactly determine the area. Exact, I will not. But at least I have tools to estimate it. Leftmost point, rightmost point, midpoint. So obviously, if I ask which of these 3 methods is the best for this function, I'm sure you all know, you're going to say the midpoint is the best estimation. Okay, now here it is. Here's a question for you, because this is what we've been doing the entire semester. Here's my question. We used 2 subintervals, and we got these rough numbers. What if I move to n equals 4? Question, if I have 4 subintervals, base, which will be now 0.5, times height, plus base, 0.5, times the height, plus base, and let's say I'm illustrating with the rightmost point. Question, will I get a better estimate of the actual area or not if I use 4 subintervals? Will I get a better estimate or not?
Yes.
Perfect. What about if I move to 8? Will I get a better estimate?
Yes.
What about 16? What about 32? What about 64 subintervals? Where am I going? Better and better.
Diminishing returns.
Say that again.
I said with diminishing returns.
Good. But what am I getting at? If I'm increasing n to 2, 4, 8, so on and so forth, what am I really getting at? What concept we studied in this class so far in which we increased to whatever?
Infinity.
In infinity. What concept is that we used over and over in this class? What is it called? When you look at it, exactly, it's the concept of the limit. When the number of subintervals increases to infinity, of what? What is this? Of what? So, and this will equal the exact area. So if I manage to fill in everything with infinitely many, oh, how is that possible? We'll talk about it in a moment. If I manage to fill this in with infinitely many subintervals, I will get guaranteed no approximation. This is an approximation. This is not the area underneath. This is not the area underneath this graph. We will be able to determine it hopefully by the end of the day today. So it's the limit of what? Of base times height plus base times height plus base times height plus base times height. Base times height plus base times height plus base times height. So I'm going to write it like this. Sum of areas of rectangles under the graph. So if I make the sum of the areas of all rectangles under the graph, if I determine the sum as n approaches infinity, the number of subintervals approaches infinity, I will get the exact area. And now we're getting into another concept, which is this. And basically the sum concept. So we have to stop and talk about the sum, and then we'll come back. What is this? Sum. Well, there is a special notation. Okay, I'm on page 9. How am I doing with the video? Okay, I have to stop.